Hello and welcome to Late Night Code. My name is Ian Riley and I'm bringing to you another problem from that ICPC North American Regional contest that took place this last February. The problem is called Hunt the Wumpus. It is the last problem in the easy category, which means that when we're done with this problem, we are going to be ready to finally move into the medium difficulty of problems. Now, you probably noticed from the light behind me that I'm in fact recording this in the middle of the day. The reason for that is because I actually tried to record it last night, only to find out today that my microphone wasn't actually reading anything, so I had to completely scrap the recording. It was totally on me. I had unplugged it and then plugged it back in, and when I did that, OBS then moved from my Yeti mic to a default. Now, the default mic for my system is the Yeti mic, and it's currently plugged in. I don't really know exactly why it still could read that data, but just be aware that whenever you disconnect the mic and you got OBS, you do need to reconnect it and then reconfigure in settings, just to be sure. I will be checking my mic before every video from now on forward. But with that out of the way, let's go ahead and jump into the problem that we have for today. Hunt the Wumpus. Hunt the Wumpus is a game you play against the computer on a 10 by 10 grid. At the beginning of the game, 4 Wumpuses are randomly placed on the grid with no 2 sharing a location. You need to find and capture all 4 Wumpuses. You guess a square by entering the coordinates as 2 decimal digits. If you correctly guess the location of a Wumpus, you are told you did so, and that Wumpus is captured and removed from the grid. Whether or not you hit a Wumpus, the Manhattan distance between your guess and the closest Wumpus is reported to you. You can use this to locate and find each Wumpus. The game ends when the last Wumpus is captured. You've been asked to write the computer portion of the game. User guesses and randomly generated Wumpus locations are defined by a 2-digit number, where the high digit is X and the low digit is Y for the point XY. To make the game deterministic, we will use our own pseudo-random number generator with a supplied seed S. Each random number is generated by first setting S equal to S plus the floor of S over 13 plus 15, and then returning the 2 low digits of S. The first 4 distinct numbers generated by this process are the locations of the 4 Wumpuses. For a seed of 132, the first location is given by the 2 low digits of 132 plus 10 plus 15, which is 57, and corresponds to the position 57. Input. The first line contains a single integer S, the seed for the random number generator. S is between 10 to the 4th and 10 to the 6th. Each of the remaining lines contains a 2-digit number, possibly with leading zeros. These are the guesses that a player has made, each corresponding to a single grid location. The input will always be well formed and will describe a complete game. The last user guess will always find the last Wumpus. There will be at most 250 guesses in any input. Output. Output the computer's response for each player guess. If a guess hits a Wumpus, you should output "you hit a Wumpus" on a line. Whether or not the player hit a Wumpus, if any Wumpuses remain uncaptured, output the Manhattan distance to the closest remaining Wumpus. The Manhattan distance between 2 points x1, y1 and x2, y2 is the absolute difference of x1 minus x2 plus the absolute difference of y1 minus y2, and will therefore always be an integer. At the end of the game, report the total number of moves M required to locate all the Wumpuses by outputting "your score is M moves" on a line. Wow, that is a lot to unpack. You know, there's typically problems like this in ICPC, almost one in every contest. I typically like to refer to them as like game problems. They'll typically have you simulate a game or enact some portion of a game, or they might give you a puzzle that has to have a solver written for it, like you'd have to write a Sudoku solver, and there's many other classic puzzles like that. And what's kind of funny about these is that when you're doing them in a contest on a timer, when you have, a dozen problems to solve in only a few hours, you'll see these problems and you'll always know that it's one of them because every problem will have like a half page to like 3/4 of a page of prompt. And then you get to this one and it'll be like a page and a half to like 2 pages of prompt. It's just the longest, it's the longest problem in the packet that they give you. And quite literally, a lot of times when you go to work on these problems, in the very the several minutes of reading the problem and understanding it, you probably could have already submitted a solution to a different ICPC problem. And so you largely just ignore these and then kind of come back to them at the end. Although you generally don't have time to, because at the end you're still already deep in another problem, trying desperately to get it submitted, and you just use up all of your time and can never really quite come back. In fact, I distinctly remember one year where I had one of these and we never got to come back to it. And then I began to wonder, what do people do when they go compete at world finals? The people who are the best at ICPC, what do they do with these problems? And I went to go look at the submitted solutions to the ICPC World's Finals problem. So again, submitted solutions that the contestants submitted during the contest. And there was only one problem in all like 12 or 13 problems that had no submitted solutions during the time of the contest. And it was the one game problem. And it had this like 2-page prompt on checkers, and you had to go through this, and there was a bunch of it packed in, and just everyone just skipped it. Just literally everyone skipped it. And so it was just cracking me up because I'm sitting there thinking, man, every single time I encounter one of these, I just skip it. What did the best in the business do for ICPC? And sure enough, they just skipped them too. But hey, you know, one of the things about this particular format though is we're not on a timer, which means that we can actually have fun understanding and digesting these problems and actually breaking them down and working through them together and just overall enjoying the theme. In many ways, these kinds of problems do actually have the most theme packed into them. And for that reason, they can be pretty fun. But again, when you're on a timer, it's really not the problem that you want to work on. So, hey, at least we get to do it here, right? Well, with that, let's start unpacking the problem. And I'm going to do this on Excalidraw, because if you're actually ever able to, if you have a notebook or a whiteboard, if you're ever doing this as a part of a contest, or if you're in a technical interview, you should try to always summarize the prompt that you've been given, summarize the question you've been given in your own words, and typically in note form too. So we're going to do that here with Excalidraw to just better understand what we've been given. So first things first, we know that we're told that there's some type of 10 by 10 grid, where this 10 by 10 grid will have cells where 4 Wumpuses will be located. And we can think about this like as a game of like almost Battleship, where the player doesn't know where the Wumpuses are. They just have to guess coordinates on this grid, where the coordinates are 0 through 9, 0 through 9. Now, fortunately for us, we don't have to be the player. We don't have to make the guesses. We just have to obey the computer here and actually generate the locations of the Wumpuses and then process the user guesses. Now, in our particular case, it's not clear yet whether or not we'd actually even need to have this grid in memory. But even if we do, it's 10 by 10. So it's a really, really small grid and could be easily stored in memory. Now, given that 10 by 10 grid, we're told that we need to be able to store 4 Wumpuses, where these Wumpuses are all going to be of the form x, y. So that's a coordinate. And so you can imagine we have like an x0, y0, x1, y1, x2, y2, and x3, y3. So those would be our 4 Wumpuses. Now, how we get those Wumpuses is then we're told that we're going to be given a seed, which I'm going to call S0. And they give us an example of this seed where they tell us like 132 is an example seed. And then from that seed, we can generate a next seed. And then from any given seed, we can take the 2 least significant digits. Effectively, the tens digit gives us the x coordinate, and the ones digit or singles digit gives us the y coordinate. But how would we go about generating next seeds? Well, they give us a formula for that. They effectively tell us that the seed Si is equal to Si minus 1 plus the floor of Si minus 1 divided by 13 plus 15. So using that, if we were to take in S0 as 132, and we wanted to generate S1 from that, we would have 132 plus 132 divided by 13 floor of plus 15, which would then give us 132 plus 10 plus 15, which would give us 157. And we're told here then that the tens digit 5 becomes the x coordinate, and the single digits 7 becomes the y coordinate. The next thing that they also tell us is that we have to have 4 distinct locations. And so we effectively need to have it be the case that each Wumpus is distinct. And they're very clear about that, which kind of makes me think that, and I actually do know because I've already recorded this, that some of the seeds will actually have non-unique singles and tens digit. Effectively, we could generate 2 distinct seeds, but their singles and tens digits are the same. So when we extract those digits, we'd get the same coordinates. If that were to be the case, then the thing that we would need to do is just ignore those coordinates and then reuse that seed to generate the next one and just keep generating seeds until we finally find a coordinate that's not been used before. So after we get the 4 distinct coordinates for these Wumpuses, then what would come afterwards is that we would need to be able to process user guesses. Now, when we process user guesses, they're going to come in as 2 digits, a tens digit and a singles digit. So once again, we can just extract the tens digit as the x coordinate and the singles digit as the y coordinate, and then just check to see if we have a Wumpus at that location. This in turn implies we probably do want to go ahead and use that grid, because it's going to be a lot easier to figure out if a Wumpus exists at a certain location if we just have the grid and we could mark ones where the Wumpuses are located and zeros otherwise. So when the user guesses, we can just check that row and column coordinate to figure out if there's a Wumpus there. Now, then the next thing after that is we need to go ahead and report a hit. So if there is in fact a hit, we need to report one. And then if there are any Wumpuses remaining, right? So then if the number of Wumpuses is greater than 0, then we also need to report a distance, which in this case is going to be a Manhattan distance. And then at the very end, whenever there are no more Wumpuses, so whenever the number of Wumpuses is equal to 0, then we also need to report the moves. And these are effectively all of the things that we need to do as a part of this problem. And most of these make a lot of sense. For example, we already have the formula here for the seed. We know how to process one. We can use the grid, in fact, to determine if seed coordinates are unique by just checking if we've already placed a Wumpus there. And so we effectively could use a count to count how many unique Wumpuses we've placed. To process user guesses, we just take them in and get the XY coordinates. To report a hit, we just check the grid to see if a Wumpus is there. We can clear it off if it is and report that hit. If we need to go ahead and report the distance, well, then we probably want to go ahead and store the Wumpus's coordinates distinct from the grid. So we'd have ones in the grid where they're located, but a separate array of their coordinates. So that way we could actually just iterate specifically over the Wumpus coordinates to figure out which one is uncaptured and also closest to the coordinate our user gave us. We could also keep track of exactly the number of guesses we're given. We're told that the last guess will capture the last Wumpus, and there will be no more guesses after that. So we can just count the number of guesses, then we'll also know the number of moves. The only question that's really left open here is how we would actually go about getting our X and getting our Y coordinates. I've said that the X coordinate is in the tens digit and the Y coordinate is in the singles digit, but how do you actually get those digits out of a number? And this is actually where modular arithmetic and integer division can be hugely helpful. Let me go ahead and give you an example of just a number like 1, 2, 3, 4, 5, 6. And let's imagine for a second that in this number, you want the value of 1, 2, 3, or 4, 5, 6. You specifically want one group of 3 digits. Let's look at 4, 5, 6 first. How would we get specifically the 3 least significant digits out of this number? If you ever want to get least significant digits out of a number, then what you need to do is take the mod of 10 to the power of the number of digits, which I know is a bit of a mouthful, but it basically works like this. There's a simple little trick. If you want the right-hand digits, you are going to use a mod, and then you're going to put a 1, and then you're going to put a 0 for every single digit that you want. So in this particular case, we would put 3 zeros because we want 3 digits. And you can look at the pattern here. Effectively, if you want 3 rightmost digits, then you take the mod of a number with 3 rightmost zeros. But why does this work? Well, modulo is always going to provide you with remainder after division. And if you look at this number, because there's a ones in the thousands place, and on the left-hand side, we have the number 123,456, then that means that this number is actually some multiple of 1,000, that being 123, plus a remainder of 456. So the remainder is always going to line up in this case with the zeros in that mod number. And since they're going to line up with those zeros and be the remainder, they are going to be the value that's going to be reported back when we do this mod operation, and we are going to get 456. Alternatively, if you want the upper digits, so now if we go ahead and look at the upper digits 1, 2, 3, then we're going to use integer division to do the exact opposite of what we just did with modular arithmetic. So where modular arithmetic would allow us to preserve rightmost digits, integer division, which we'll use a double slash for that, which is the Python operator for it, but I like it as a shorthand for floor. If we do this here, then we can follow the same pattern and now do integer division 1000. But rather than preserving the digits that line up with the zeros, it instead eliminates the digits that line up with the 0. And this should make sense because integer division does not keep any remainders. So the remainder must be eliminated. And if the remainder in this case is 456, it has to be eliminated. But what would the integer division report? It's always going to report that coefficient factor that you multiply 1000 by in that formula. Okay. Now, again, if you're not very familiar with this formula that I'm talking about, that formula basically looks like this, which is basically to say that 1, 2, 3, 4, 5, 6 is equal to some d times 1000 plus r, where r is the remainder. So this r value is what's going to come down here when we do the modulo, and this d value is what's going to come down here when we do integer division. And what's that d value? In this case, it is 123 because the number is 123,000. So it's 123 times 1,000 plus 456. So now we're going to get that 123. Effectively, again, if we want the upper 3 digits, that's the same as saying that we want to eliminate the lower 3 digits in this case. And to eliminate the lower 3 digits, or the 3 rightmost digits, we do integer division by a number with 3 rightmost zeros, 1000. Now, I keep saying a number, but just to be clear, it needs to be 1 followed by the number of digits. It has to be a power of 10 for this to work with a decimal system. So that's how we can actually get specific digits out of numbers, and you can use them in combination. So for example, now taking our number of 157, if we want to get our x coordinate, then all we would need to do is grab the 2 rightmost digits. So if we want to grab the 2 rightmost digits, we're going to do a mod of 100. Afterwards, we now have the number 57, right? Because we grabbed those 2 rightmost digits. But what we really want in this particular case is the 5. Well, now that we've grabbed the 2 rightmost digits, all that's left is to eliminate the rightmost digit. And so now we would then do integer division by 10, and that's going to give us 5 because it'll eliminate the 7. Similarly, if we want y, which in this case is going to be the single rightmost digit, then we just need to preserve 1 digit from the right, so we would do mod 10. And so that's how we can actually get the x-coordinate of any seed, regardless of its length, and the y-coordinate of its seed, regardless of its length, just by doing these 2 simple formulas. We can also do a shorthand of these formulas for our user guesses, because our user guesses are only 2-digit numbers, which means that we can just go ahead and integer division by 10 to get their x-coordinate, and mod by 10 to get their y-coordinate. And just to go ahead and clarify, once again, that is the x and that is the y. So I believe that covers all of our necessary steps and all of the necessary ideas and logic that we would need to incorporate in order to solve this problem. So with that out of the way, let's just go ahead and jump in and actually start working on this problem. Okay, so now we're in the Hunt the Wumpus file and we're ready to start working on our solution. So let's start going through the steps as we remember them. The first thing that we were told from our input is that we're going to be given a seed value, which can go up to 10 to the 6th. So I'm going to go ahead and store a seed value here. It's going to be mutable. So we'll say let mut s. We're going to go ahead and use our helpers for a next, and we'll use a u32 because we know it's a non-negative integer. And since it can get up to 10 to the 6th, it'll be a u32. At which point I'm going to go ahead and pass in a string buffer. Now to make things easier on myself, I'm going to go ahead and actually declare that buffer. I say easier on myself. This isn't really easier on me, but this is going to be better because we're going to be taking in several different strings. They're going to be parsed out to numbers. So we're better off not just allocating strings all the time, but just reusing the same buffer. So we'll go ahead and pass a mutable reference to that buffer, and now we have our seed. Once we have our seed, then our next job is to go ahead and generate 4 unique sets of coordinates. So we're going to go ahead and have a let mut count, which will keep track of the number of unique coordinates. And we're going to say while count is less than 4, which is exactly the number that we need, then we can now use our formula to compute the next s, where s is plus equal to s integer division 13. This is integer division because it's between 2 integers, plus 15. Now we have s, and we can go ahead and compute x and y by using our formula, where x is now s mod 100 divided by 10, and y is going to be mod 10. Okay. Now, once we have those coordinates, then the next thing that we would need to do is fix our typo. There we go. We need to actually see whether or not we've generated these coordinates before. To go ahead and do that, I'm going to come up top over here and say let mut grid, and I'm just going to go ahead and declare a 10 by 10 grid. Now in this grid, we're only storing zeros and ones. So I'm just going to go ahead and have these be U8. So we'll just say 0, U8 for all of the values. There's 10 values in a row. There are 10 rows. And now we have that 10 by 10 grid. So once we generate an X, we can just simply say if the grid X as U size, Y as U size is equal to 1, that means that we've actually generated those coordinates before, and we just need to do a simple continue to skip this iteration of the loop. Otherwise, then what's happened is we've actually, if I can go ahead and do this, there we go. Otherwise, what's happened is that we actually need to store a Wumpus at the location. So we can go ahead and say here, if I can go ahead and get that over, that this grid X as U size, Y as U size is actually equal to 1 to now represent that we have stored a Wumpus there. And I can go ahead and increment our count. So this would actually be able to get 4 unique sets of coordinates and be able to store them in a grid and know when it's actually stored 4 unique coordinates. But one other thing that we had mentioned is that we would need to be able to compute distances to Wumpuses that haven't been captured. And the better way to do that is to actually know the exact positions of the Wumpuses to begin with. So we're going to go ahead and say let mute Wumpuses equal to, and we're just going to use coordinates here, and we're going to use 4 of them. So I'm going to have a 0i8, 0i8, and we'll go ahead and have 4 of those. Now I'm going to use i8s here because effectively these are going to be quite small. They can only be 0 to 9, but we're going to be using these for Manhattan distances, and you can't do Manhattan distance with an unsigned number because it can never be negative. And Rust is very pedantic about your use of unsigns. If you do one unsigned number minus a larger unsigned number, you will get an error. So instead, we'll do i8s here, and that will be sufficient for our purposes. So now after we've stored this location in a grid, we can actually go ahead and just say that the Wumpuses at count, because that is the Wumpus we're storing, is now equal to a tuple of X as I8, Y as I8. And we've already shown to ourselves, at least through ScalaDraw, that these are single digit numbers, so we're fine here. Plus, if they're not, it's going to break our grid. Okay, so now we actually have our 4 unique seeds with 4 unique coordinates stored in the grid as ones. The count is 4, and all of our Wumpuses have been stored. So the next thing that's going to happen is that we're going to go ahead and get our user guesses. And our user is going to keep guessing until they capture the last Wumpus. So we can just use our count variable again. We could say while count is greater than 0, we're going to go ahead and start getting those guesses. First thing you got to do is clear off that buffer. And then we can go ahead and say let guess be equal to next. And then this would actually be a U8 because it's just a 2-digit number. We can pass in a mutable reference to that buffer. Now that we have the guess, we can go ahead and say let xy be equal to, and then just guess divided by 10 for the x coordinate, guess mod by 10 for the y coordinate. And then I'm going to go ahead real quick and come up 11 and go and grab this line and go ahead and paste that down here because I want to go ahead and ask the question now if the grid X as U size, Y as U size is equal to 1. Because if it is in fact equal to 1, then that means that this particular guess has actually hit a Wumpus. At which point we would go ahead and do a print line of U hit a Wumpus, exclamation mark. We can go ahead and double check on our prompt that that's the case. You hit a Wumpus, exclamation mark, looking good. And then afterwards, we need to start mutating some of these properties. We need to go ahead and mutate our grid and our count. For our grid, then we'll go ahead and do this one real quick. Just copy that one, paste that one below, and then we'll go ahead and shift this over by one more. And we'll set that equal to 0. Still getting kind of used to using all the Vim bindings because I've used Vim for a long time, but I always just stayed in my comfort zone and never really challenged myself to be more efficient with it. And now that I have, I'm starting to realize how much more I can do, but also how much I was really just stupidly ignoring before. But yeah, so getting used to it and having fun doing that on this channel as well. Okay, but back to the problem. So we've gone ahead and marked this grid as being 0. So that's gone ahead and cleared out the Wumpus. It's like it was never there. And then the last thing we need to do is just decrement our count. Okay. Now it's possible that after hitting this last Wumpus and decrementing the count, that we've actually captured the very last Wumpus. So if that's the case, if the count is now equal to 0, then we're just going to go ahead and break out of this loop. Now, if the count in this particular case is greater than 0, which means that there's still some Wumpus remaining, then the next thing that we're told that we need to do is go ahead and print the distance to the nearest Wumpus. So to do that, we're actually going to lean into the wonderful Rust iterators. So we'll go ahead and say let distance be equal to Wumpuses. We'll go ahead and get those Wumpuses iterators. And then with that iterator, what we can do is a filter and map. So I can go ahead and say filter on the Wumpus. And what I want to do is check if the grid of Wumpus.0 as usize, Wumpus.1 as usize is equal to 1. And so what that means is that I want to keep every Wumpus that currently is still in the grid, but ignore all the ones that are not. Once I've filtered out to only the Wumpuses that are in the grid, then I can go ahead and compute their Manhattan distance by mapping the Wumpus to a Wumpus.0 minus x as I8 dot absolute value plus the Wumpus.1 minus y as I8 dot absolute value. So this now maps those Wumpuses that are uncaptured to their Manhattan distance. Through this iterator, I can then go ahead and ask for the minimum of all such numbers. This will be an optional over that I8. So just keep in mind that it is an optional because an iterator is not guaranteed to have any values. The filter could have cleared them all. We know that there is going to be a value because there must be at least one Wumpus still in the grid. So we can just go ahead and unwrap that result and then go ahead and do a print line of that distance to report that distance. The only other thing that's remaining for us is that we need to be able to count the number of guesses. So we'll say let mut m equal to 0, and then every single time that we get a guess, I'll just put that here, we'll say m plus equal to 1. Okay, so that way we can actually count the number of guesses. And then at the very end here, we can just go ahead and print off, print line, your score is m moves dot passing in the m. Okay, and that's looking pretty good so far. So the next thing for us to do is to go ahead and get our sample input. There's no test cases on Sir Judging for this one, so we're just gonna have to rely on Caddis. Okay, so let's go ahead and open up a second window here, and let's go ahead and come over to Caddis and grab our sample, and then we'll go ahead and clip P that into cargo run --s, hunt the Wumpus, and let's see what we get. And we got 111, score is 4 moves, which is exactly what we expect. Let's go ahead and grab the other one. And we get 42815, your score is 6 moves, which is exactly what we expect. And with that, since there are no test cases on Sir Judging, the very next thing for us to do is go ahead and upload this file. And let's see what we get back in terms of the results. Okay, and with that, you can see that we passed all the test cases on Caddis, and we've knocked another problem out of the park. That brings us to the end of the easy problems in this contest. I hope that you've enjoyed them. The next episode that we're going to do is going to be a bonus episode where I go back through these and explain the Rust code that we used to solve them. So to do a bit more of a deep dive into the language itself, I'm going to show off some of the really cool things that Rust is doing for us under the hood. But until then, I hope that you enjoyed this one and that you have a great night.